This is still example 3 from section 4.5. I just got booted off my connection. My internet gave out in the last video. So here's the rest of the problem, hopefully. So we had just gotten to this point right here where we had figured out an expression for x. So x equals 2 times the square root of 4 minus y squared. And so now we're going to take that and put it into our area equation for the rectangle. If you'll recall, we were looking at this rectangle inscribed in an ellipse, and we had just gotten that x equation from the equation of the ellipse itself, and we needed to take that and use it in order to make our area function into a function of just one variable. So we're going to take that area equals 4xy and plug in the fact that x equals 2 times square root of 4 minus y squared. So here it is, we just put in our new expression for x. Okay, now let's clean that up a little bit. That would be 8y square root of 4 minus y squared. Or since we know we're going to need to take the derivative of this function, let's go ahead and rewrite it as a equals 8y times 4 minus y squared to the 1/2 power. Okay, so that will allow us to take the derivative of the area function. And noticing again that the area function is all in terms of just one variable now. It's only y, not a mixture of x's and y's. So we'll be able to do a prime, or this would be dA dy, by the way. We will need to use a product rule because we have the product of two functions, 8y times this 4 minus y squared to the 1/2 power. So product rule time, here's our first function. And then the derivative of that second one is going to take a little bit of chain rule. So bring down your 1/2 blank to the negative 1/2 power. Okay, 4 minus y squared goes in there. Multiply by the derivative of the inside. Okay, so that'd be the derivative of 4 minus y squared, which would just be negative 2y to the first. Okay, so there's our first function times the derivative of the second plus our second function times the derivative of the first, which is just going to be 8. Okay, so cleanup time here. Notice in our first term, we can do a little bit of cancellation here. 1/2 cancels with the 2. And so we have still that negative. Okay, don't lose that guy, it's important. So we would have negative 8, and then we have 1y here and another y here. Okay, so negative 8y squared, and then 4 minus y squared to the negative 1/2 power. And then add our second term, 8 times 4 minus y squared to the positive 1/2 power. Okay, and you might be able to see that we can do some factoring there. All right, we can factor out an 8, certainly, and then factor out your lowest power of the other shared factor, 4 minus y squared. The lowest power would be the negative 1/2 power, so we'll factor that out. All right, and see what's left over. In the first term, we've factored out this whole part, and we factored out the 8, so we're left with negative y squared. And then in our second term here, we factored out the 8, and then when we take 4 minus y squared to the negative 1/2 out of 4 minus y squared to the positive 1/2, you're going to divide this by this that we factored out. You'd subtract the exponents, so you end up getting 1/2 minus negative 1/2, which is just going to be 1. So we just have 4 minus y squared to the first power. Okay. And let's continue our cleanup here. All right, inside here we have negative y squared plus another negative y squared. So that would be negative 2y squared plus 4. All right. So let's get this into a rational format. That way we can look at our critical points. So up in the numerator, we're going to have 8 and negative 2y squared plus 4. And down in the denominator, we'll have our 4 minus y squared to the 1/2 power now, slipping that down into the denominator. Okay. Now you could even do a little bit more simplification there. I'm noticing that we could factor a negative 2 out of these terms. So really just taking it all the way here. So negative 16 and then y squared minus 2 over, I'll write that as the square root of 4 minus y squared. Okay, so there's our expression for the first derivative. Now we need to find critical points of this. Okay, so critical points. First, let's start off with where our derivative would be undefined. That would be if the square root of 4 minus y squared equaled 0, which would lead to 4 minus y squared equaling 0, y squared equaling 4, and so y equaling plus or minus 2. Okay, now there's something a little bit special here. So let's see. Oh, okay, never mind. We're all good. Those are kind of interesting points though, because take a look back at our picture real quick. In the y direction, notice how the farthest our ellipse goes is to plus or minus 2. So actually, those critical points, quote, quote, critical points that we just found, those are actually endpoints of our domain for this, or the interval of values that we could potentially have. So let's kind of note that on the picture here. Okay, because of those points, y must be strictly between -2 and +2. Notice how if y actually equaled either one of those, our rectangle would shrink in like this, okay? Because the y direction would take up everything. The rectangle would look more like just a vertical line, and there would be nothing in the x direction. So we know that that is actually not going to be an ideal situation to find our maximum area. So we want y to be somewhere between, but not actually equal to those values. Okay. So let's see here. Let's mark those as endpoints. And also make a little note that they're not physically realistic. Physically realistic. So let's focus instead on our points where a prime equals 0. That would be where our numerator, -16 times y squared minus 2 equals 0. that would give us y squared equals 2. And so y would equal plus or minus the square root of 2. And that seems a little bit more realistic because that is actually inside of the range of plausible values there. Okay, so we have gotten 2 critical points here. Okay, so we need to test which one of those is really going to give us the maximum area that we want. So let's test. Let's make a number line for a prime. Let's put our negative root 2 and our positive root 2 on there. And I'm also going to put 2 and negative 2 just as some boundaries, because none of these values outside of that are going to be realistic. Okay, you might also notice if you picked some value in that area, like if you picked y equals 3, for instance, that would not jive very well with the denominator of our derivative. You'd be getting a negative underneath that square root, and we don't want to work with complex valued functions here. No, thank you. So we are not even going to consider that realm of values that are greater than positive 2 or less than negative 2. But we can test things within these intervals here. Okay, so I'll leave most of the calculations for you guys to test out, but you'd end up getting a positive denominator and a negative numerator for any value in this interval. So that'd be a negative first derivative. In this middle interval here, you would get, again, a positive denominator, but a positive numerator here. Maybe pick a value like 0 in there. Positive first derivative. And then here in this interval, you'll get positive denominator and a negative numerator again. So we're back to negative first derivative. So our area function is decreasing and then increasing and then decreasing again. So of those 2 critical points, negative square root of 2 is not going to be what we want. We want positive square root of 2 to give us a true maximum value for this area. So this will give us a max. Okay. And so got the right there. Let's see how they want the answer formatted. Okay, it says what are the dimensions of this rectangle? Okay, and the overall dimensions are 2x by 2y. So we'll need to find those values. Okay, and we just found that we want y equals positive square root of 2 to give us a max for our area. And we can use that in turn to find what x is going to be. Okay, so x is, from our equation right up here, x is 2 square root of 4 minus y squared. Okay, so x equals 2 square root of 4 minus y, which is square root of 2 squared. I am so running out of room on this. Maybe you are too. Okay, but we'd have 2, and then underneath that square root would be 4 minus 2. So 2 root 2 for the x. So for our overall dimensions of the rectangle, it's going to be 2x by 2y. So 2x would be 2 times 2 root 2. So many 2's there. Okay, so 2x is 4 root 2, and then 2y would be 2 root 2. And that is going to be our final answer for this maximum area rectangle.